Fine. So let us start. Do you have any questions? Any questions? Okay. So we are done with the continuity equation. So today we are going to deal with the boundary surface and, if possible, verticity and vertex lines. Right? Okay. So boundary surface, we mean, suppose if there is a boundary to the fluid, then what is the direction of the fluid flow? Let us say there is a dam that was constructed. This is a big wall. And then there is a fluid flow that is happening till this point. Now exactly at this particular point, what is the direction of the fluid flow? What is the direction of the fluid flow? In which direction fluid particles will move at the boundary? Anybody? Any idea? Is it normal to the surface or tangential to the surface? Because that is a fixed boundary. If it is a fixed boundary, there is no possibility of moving further. So exactly till this point, whatever may be the direction of the fluid that is coming, but here these fluid particles, once it touches the wall, it will go tangential. At any instant if you take it, it will always be a tangential to the surface. Got it? But what if there is a movable boundary? Movable boundary means a boundary movable boundary, we mean, suppose take the balloon. So when you are pushing the air into the balloon, then there is a boundary, but the boundary is keep on expanding. That means there is a change that is happening to the boundary itself. In that case, the fluid particle or the air particle, whatever is moving, will be exactly perpendicular to the surface for the direction, right? Take one more case. Suppose if there is an oil and there is a water, both are mixed together. So these two will be in contact with each other. But if the fluid is moving, then this boundary surface which is dividing these two, suppose, let us say, so this is the boundary, and let us say this is water and this is oil, and this is the boundary surface. And this boundary surface, if this water is moving this way, then the fluid particles that are going to travel will be normal to the, so the velocity of the fluid will be normal to the surface. Got it? So this is a movable boundary. Here there are two cases. One is the velocity of the fluid, another is the movement of the surface. So let us say this is traveling with a velocity of u, and then this is traveling with a velocity of q. Fluid is traveling with a velocity of q, and the boundary is also traveling with a velocity of u. Then ideally, as per the continuity equation, both should match. So the normal component of velocity is q dot n, and the normal component of the surface velocity, so that is u dot n. These should be equal, or the difference should be same, or q minus u dot n is equal to 0. So this is the fundamental condition. So this is velocity of the fluid. And this is boundary velocity. This n is unit normal vector to the surface. Got it? Unit normal vector to the surface. Now, if you wanted to identify whether it is a possible boundary condition or not, or the boundary surface or not, let us say, suppose if the boundary equation is f of x comma t is equal to 0. So this is equation of the boundary. So this is the equation of the boundary, and then suppose at later time the position will be x plus delta x or r plus delta r comma t plus delta t. Now this is the new position of the boundary. Then obviously if you expand this f of r plus delta r comma t plus delta t equal to 0, and this expansion, if you make it with the help of Taylor's expansion, use Taylor's expansion. So Taylor's expansion, if you use it, then this will be f of r comma t plus dou f by dou t into delta t plus dou f by dou r. So here r is a vector that you have to be aware. Dou f by dou r into dr, and this is equal to 0. So higher order terms you can neglect because dr and dt will be almost tending to 0. And then so f of r comma t is equal to 0, which is the original boundary condition. So this you can replace with 0, and then df, so dou f by dou t plus, so dou f by dou r, so this is what we call as del f, because this is nothing but r is a vector. When you are doing a derivative with respect to vector, it is nothing but del, right? So by definition this is the del. So del f into delta t delta r, delta r divided by delta t. So as delta t and delta r are almost tending to 0, this you can replace with dr by dt. So this will be dou f by dou t plus dr by dt into del f. So here, so del f. So here there will be a dot because r is a vector and f is a vector. Straightforward multiplication is not possible. Got it? So this is equal to 0, and this is nothing but the boundary condition. Boundary condition. So this is the boundary condition. So if you are given a surface, and that surface, if you wanted to identify whether it is a possible liquid surface or not, this is the condition that needs to be satisfied. So dou f by dou t, this is capital F, dou f by dou t plus dr by dt dot del f is equal to 0. Got it? How dr by dt? See this, I have divided this delta t over the entire equation. So this delta t is coming at the denominator here. Understood, Samrin? Note down this. So dr by dt is nothing but the velocity. Let me know once you note it down. Done? Okay. So what is the normal component of the velocity? normal component of the velocity. Okay, so this boundary condition what we have got is dou f by dou t plus dr by dt dot del f equal to 0, or dou f by dou t plus q dot del f equal to 0, since q is equal to dr by dt, because this is nothing but the velocity of the fluid. So this is the boundary condition. Then dou by dou t plus q dot del of f is equal to 0. This is nothing but the material derivative should be vanished. This is as simple as this. So the substantial derivative of the function, which is the boundary condition function, should be equal to 0. Then we say this is a possible liquid surface. Clear? Understood or not? So normal component of the velocity. Of the velocity is nothing but q dot n. So this is the normal component of the velocity, where n cap is the unit normal vector. This unit normal vector you can find out from the boundary surface. The n cap is equal to del f divided by mod del f. I hope you are aware of this. So del f by mod del f will always give you a normal vector to any surface. So del f is the normal vector, unit normal vector, unity divided with the mod del f. So normal component of velocity So this normal velocity will be q dot del f by mod del f. But from this equation, q dot del f is equal to minus dou f by dou t. And this you can replace it here. Q dot del f can be replaced with minus dou f by dou t divided by. So del f mod is nothing but dou f by dou x whole square plus dou f by dou y whole square plus dou f by dou z whole square under root. So this is the normal component of the velocity of the fluid. Clear? Why we are concerned about only the normal component of the velocity is because this is a moving surface. So the velocity of the moving surface can be identified perfectly with the normal component of the velocity. Got it or not? So all these things are coming into picture if there is a boundary but between two different kinds of surfaces or two different kinds of material. Suppose if there is oil and water, or if there is a wall and the water, if there is a air and wall, so air and water. So these are the kind of places wherein there is a possible kind of surface. So there is a change in the material that is happening. If there is a change in the material, then the surface on top of this. So what is the boundary condition there? So that boundary condition is verified based on the material derivative. If it is equal to 0, then that is a possible boundary surface, or else it won't form as a surface. Got it? So it may be a fixed xyz coordinates, or it may be a function of xyz alone, or it may be a function of xyz and t also. So if it is a t, then it is a movable boundary. If it is xyz itself, then it's a space boundary. Clear? Okay. So note down this. So I think, so based on this concept, I think there were multiple times actually questions were asked from this aspect. So we'll solve one problem which was given UPSC already. Note it down. Note down this problem on the boundary surface. Show that, I think so before that I will discuss what is the velocity potential and the vorticity. So vorticity means possibility of having rotational flow. So this is vorticity, right? So vorticity means there are two different kinds of flows. One is the fluid can go in a linear manner, or the fluid can flow in a circular manner, right? So the circular manner, so whether it is going in circular manner or not, this can be identified based on the vorticity. So for that, the vorticity can be found that is del cross F or del cross Q. So as I explained earlier, if del cross Q is equal to 0, then we say this as irrotational flow. So this is irrotational flow. What if it is not irrotational flow? That means there is a rotational component, right? So del cross Q is not equal to 0. This is rotational flow. So this is the rotational flow. So irrotational flow and rotational flow. So this flow is also called as potential flow. And this flow is also called as vortex flow. Right? So suppose if there is a water moving in the canal and exactly near the dam, there will be a kind of circular curls that are going to be coming, right? So those curl, in which direction the fluid is moving there, those fluid particle lines or the path traced by those fluid particles we call as vorticity. So in case if there are no vertex lines, that means there is no circular flow. If there is no circular flow, this will be based on the potential energy difference between them. It is going to move in a linear fashion, right? So that's why the entire fluid flow is divided into two parts. One is the potential flow, another is the vortex flow. This we are going to deal separately, and this we are going to deal separately, right? So this is del cross Q is equal to 0. So as per vector identity, if del cross Q is equal to 0, then Q can be expressed as minus del phi, as I explained earlier. So you can identify a scalar. Identify a scalar, so whose del phi is equal to velocity. So this scalar is called as potential. This is named as potential, right? So Q is equal to minus del phi. So del cross minus del phi. So del cross del phi is always equal to 0. So this is the vector identity. Got it? So that's why phi is nothing but the scalar potential or scalar potential. So this scalar potential you can identify first. So once you identify the scalar potential, you will always deal with only this particular scalar to analyze the complete flow. So that's what we call as the potential flow. But in case of del cross Q not equal to 0, then we call that as the vortex flow. Then suppose if del cross Q is, we know that Q is equal to Ui plus Vj plus Wk, right? So this is the q vector. Then if you want to identify del cross q, then this will be I, j, k, dou by dou x, dou by dou y, dou by dou z, and then u, v, w. So this determinant value will give the curl component del cross q. Then this will be I into dou w by dou y minus dou v by dou z plus j into dou w by dou x, dou u by dou z plus k into dou v by dou x, dou v by dou x minus dou u by dou y. Got it? So this is I into xi plus j into psi plus k into there is some standard convention to this. Xi, eta and mu. Yeah. So this is how actually usually the vertex, right? So vertex lines, so it's not vertex. Verticity components are represented. So this is the verticity along x direction, this is along y direction, this is along the z direction. So this you got it from the del cross q. So these are called the rotational components. So these are called as the rotational components. Rotational components. Here? It's not minus j. I have changed the order dw by dx and du by dz. So you can note down this. So based on this value, we will be finding out the vertex lines the way we found the streamlines. So there is nothing here. See this, q is ui plus vj plus wk and del cross q is nothing but the vertex components, right? So this is the vertex components. So del cross q, you have just done the determinant of it, which is nothing but del cross q value mathematically. Now I into dou w by dou z minus dou v by dou z, right? So sorry, dou w by dou y minus dou w by dou v by dou z. Similarly, minus j into dou w by dou x minus dou u by dou z. So that's why actually I have changed the order by taking minus out. So dou u by dou z minus dou w by dou x. And then the last step will be plus k times of dou v by dou x minus dou u by dou y. So these are all called as the vertex components or the rotational components. These rotational components along x direction is I and along y direction is eta and along z direction is mu. So these things are just named it like this. Rather than writing every time like this, we write this. Note it down. Okay. So now the vertex lines. See this. In case of potential flow, so our interest is to find out the streamlines because that is what is the essential component for us which is needed because that is the flow direction. Now in case of rotation, there is no, so the flow is then and there only it is happening and there is certain components. So suppose if the water is taking a little bit of turn for a certain distance, that turn in which direction it is going to take. So that depends on these rotational components. So it is essential to identify the vertex lines the way we have identified the streamline. Streamlines are applicable for the non-directional, so non-rotational flow, that is the potential flow. Vertex lines are applicable for the vortex flow, right? So vertex lines are nothing but the streamlines in case of rotational flow. Got it or not? Are streamlines in case of rotational flow. So in case of rotational flow, the streamlines are nothing but the vertex lines we call. So the vertex lines can be found, the verticity component vector. I think there is a name given for that. Yeah, omega. This is the letter that is used. Verticity vector. So this is verticity vector. Usually this value will be xi into I plus eta into j plus mu into k. So this is the verticity vector. Now the way we found the streamlines. Suppose if there is a fluid flow that is happening, then this is the direction of q and this is the direction of dr. Then at this point of contact where the direction of the flow and dr should be matching together, then q cross dr we found and this we equated to 0. Got it? So because these two are the parallel components. Now in case of vertex flow, the flow is in a circular manner. So if it is in circular manner, then these circular components are nothing but the verticity components. So this is rather than q, now it is verticity vector. So this verticity vector, it has to exactly match with the dr. So this is the direction of dr. So verticity vector cross dr should be equal to 0. This is the equation of vertex line. Got it? So vertex lines is nothing but the gross flow direction, gross fluid flow direction in a circular manner. So that direction is defined by verticity vector cross dr. So both are vectors here. So this is a elemental change in the space. So this will be xi into I plus eta into j plus mu into k cross I dx plus j dy plus k dz equal to 0. Now if you simplify this equation the way we have done in case of this vertex lines, so in case of streamlines, so this will be dx by xi plus equal to dy by eta plus dz by mu equal to. So this is vertex lines equation. So this is vertex lines. I'll write here itself the streamline. Dx by u equal to dy by eta, dy by v is equal to dz by w. So these are the streamlines. And this is the potential flow. This is the vertex flow. Got it? You can note down this. So vertex is rotational. This is non-rotational. Clear? You can note down this. So this is the complete fluid flow. So fluid flow is divided into two parts, vortex flow and non-vortex flow. So non-vortex flow is the potential flow. So this is the direction of the flow in case of vortex flow. This is the direction of the flow in case of the potential flow, right? So this is named as streamlines. This is named as vortex lines. So these two we are going to deal separately in upcoming classes. Clear? Any questions on this? So note it down. Okay. So based on this understanding, we will solve some problems. Note down this problem. Show that phi is equal to x into f of r is a possible form of the velocity potential. Is a possible form of the velocity potential is a possible form of the velocity potential of an incompressible liquid motion. Of an incompressible liquid motion. Given that the liquid speed q tends to 0 as r tends to infinite. Q tends to 0 as r tends to infinite. Deduce that the surface of constant speed r square plus 3x square into r power minus 8 equal to constant. And try to read the problem statement. This was given by UPSC. Understood the problem statement? I think it was given in 2010. I don't remember exactly the year, but it was given. So here the velocity potential is given. So phi is equal to x into f of r. So whether it is given or not, you have to understand that the relation is r is equal to xi plus yj plus zk. So this is the value of r in terms of Cartesian coordinates. Then r square is equal to x square plus y square plus z square. So this is the relation that you have to remember even if it is given or not. Got it? Now based on this understanding, what he said was is a possible form of velocity potential. So this is a possible form of velocity potential that you need to show. Then of an incompressible liquid motion. So incompressible liquid motion means this is del dot q should be equal to 0. So that is what is the incompressible fluid. That is nothing but the continuity equation for an incompressible fluid. Given that the liquid speed q tends to 0 as r tends to infinite. This part was given to find out the initial conditions. Then he asked us to find out the constant speed lines. So where all the constant speed is there. So such kind of points are represented by r square plus 3x square into r power minus 8 equal to c. So this is what actually he asked us to prove. Now try to solve on your own. I'll give you 2 minutes time. After that, if you are not able to solve it, I am going to solve it for you. Any idea how we can do? See this. This is what is given. Phi is the only thing which was given. Then if it has to be a possible liquid motion, then ideally Q should be equal to minus del phi. So this is one thing which you need to prove. Then the another thing is del dot Q is equal to 0. If it is 0, then it's a possible liquid motion. Got it? Understood or not? So first actually you find out what is minus del phi. So minus del of x into f of r. So it implies Q is equal to minus. So apply UV formula. This is one part and this is one part. So f of r into del x plus f of r into del x, x into del of f of r, right? So what is del x value? So minus f of r, or I just simply call, okay, f of r. What is del x? What is del x? Anybody? Any idea? We are done with vector calculus, right? So del is nothing but I dou by dou x plus j dou by dou y plus k dou by dou z. And this is operated on x. So as it is a partial derivative, these two will become 0. And this is dou x by dou x is 1. So then this will be simply I. So I plus 0 plus 0. So this will be I. So f of r into I plus x into, so del fr. So this is I dou f by dou x plus j dou f by dou y plus k dou f by dou z. But here r we are doing, so f is nothing but a function of r. But r is related to x, y, z in terms of r square is equal to x square plus y square plus z square. Then from this relation, 2r into dou r by dou x is equal to 2x. So this 2 will cancel. Dou r by dou x is equal to x by r. So this is the relation that you have to use. Dou r by dou x is equal to x by r. And that x by r, so dou f by dou x you cannot do because f is a function of r, it's not a function of x. But indirectly r is a function of x. So that's why when you are doing this, so you have to identify that dou f by dou r into dou r by dou x. So dou f by dou r is f dash of r into, so dou r by dou x is x by r into I plus y by yj by r plus zk by r. So this is del of f of r. Now that's why del of f of r usually it is represented with r bar by r into r bar by r into f dash of r. Clear? So this is a possible form of, so now actually if it has to be a possible form of liquid motion, then you need to identify del dot q is equal to 0. So del dot q you need to find it out from this and then equate to 0. Now try to do that del dot q from that equation. Note it down. Note this and then try to find out del dot q for this. So q is given. Is it noted? Okay. So finally what we have got is del phi is nothing but q minus del phi. So this is minus of f of r into I plus x into f dash of r divided by r into r bar. So this is the velocity vector. And then for proving the continuity equation for an incompressible fluid, so del dot q is equal to 0. Then del dot q is equal to del dot minus del phi. So this is minus del square phi. So this is minus del square phi. So del square phi is nothing but minus of dou square by dou x square of phi plus dou square phi by dou y square plus dou square phi by dou z square. So this is del square phi. This is easier than deriving from this q. So del dot q, if you want to do it, that is a little bit complex, but this is a simply scalar value. So this is, you can find out dou square phi by dou x square. Here phi is given as x into f of r. So this is the phi value. Then dou phi by dou x, you can find it out. This is x into f dash of r into x by r. So this is x square into f dash of r divided by r. Dou square phi by dou x square. Now derivative of this with respect to r. Now this is x square into derivative of this will be r into f double dash of r minus f dash of r divided by r square plus f dash by r into derivative of x square is 2x. So this is dou square phi by dou x square, right? Similarly, so can we simplify further? Yeah. Similarly, dou square phi by dou x square minus del square phi is equal to x square plus y square plus z square divided by r square into r into f double dash of r minus f dash of r plus f dash of r divided by r 2 times of, then this will be x plus y plus z. Is that correct? And these two will cancel out. Yeah, so I think so here there is one x by r. Yeah, see this. So here when we are doing the derivative x square into this one we are doing with respect to r as the derivative. Now this is, if you wanted to do with respect to x, then you have to do with respect to r and then do dx by, so dr by dx. This is as per the chain rule. Now r into f double dash of r minus f dash of r divided by r, and originally, yeah, so divided by r square into dr by dou r by dou x. Dou r by dou x is x by r. Yeah, got it? Then plus f dash of r by r into derivative of x. So with respect to x, that is 2x. Now here in all the places there will be one x by r also. Here x by r, right? So I'll just rewrite this. Yeah. So del square phi is nothing but dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square, and this value x cube by r square into r into f double dash of r minus f dash of r plus y cube by r square into r into f double dash of r minus f dash of r plus z cube by r square r into f double dash of r minus f dash of r plus, sorry, this is r cube. Yeah. And then f dash of r 2 times of, then this will be x plus y plus z. So this is del dot q value, right? For an incompressible fluid, this is equal to 0. So let me verify this. I think this is not matching. Yeah, so I think there are mistakes here. So here actually we didn't apply UV formula. This is one mistake. And from there I think everything went wrong. I'll just redo that. See this, phi is equal to x into f of r. Now then dou phi by dou x. So if you apply UV formula, x into f dash of r into derivative of r with respect to x. So dou r by dou x is nothing but x by r plus f of r into dou x by dou x is anyway equal to 1. So this is x square by r into or x square into f dash of r divided by r plus f of r. So this is dou phi by dou x. Similarly, dou square phi by dou x square. So this actually entire thing we have to do the derivative with respect to x again. So apply UV formula on this. If you apply UV formula on this, this is x square into f double dash of r into f double dash of r minus f dash of r minus f double dash of r divided by r square into x by r plus f dash of r divided by r into derivative of this will be 2x plus f dash of r into x by r. So this is dou square phi by dou x square. Got it? So this actually we need to simplify, and then dou phi by dou y. But dou phi by dou y will be different because you are doing derivative with respect to y. But here in case of x there is one x extra. So dou phi by dou y is nothing but x into, so you don't need to apply UV formula. So this is f dash of r into y by r, dou phi by dou y, right? So then dou square phi by dou y square is equal to, so x anyway you can take it out, then dou by dou y of f dash of r divided by r into y. So for this actually we need to be doing. Now here instead of x actually you are going to get y. So this x square will be common in all the cases. So you can take out x square out. So minus del square phi x square by r square you can take it out, and then r into f double dash of r minus f dash of r divided by r square anyway taken out, and then x plus y plus z divided by r. Plus f dash of r divided by r into 2x. So this is 2x and this is 1x. Anyway, so you try to simplify this. So this is exactly the same procedure, but finally what we are going to get it is minus del square phi is equal to minus x into f double dash of r plus 4 times of f dash of r divided by r. Yeah, so that's what you are going to get it. Got it? So will you be able to solve this on your own? So just actually finding out the derivatives and then substituting second order derivatives for the velocity potential function phi is equal to x into f of r. So here I think so with respect to x actually this is correct whatever I have done, and then with respect to y and with respect to z you need to exactly do that and then substitute here minus del square phi. Then the simplified form will be this kind of format you are going to get it. Got it? Understood or not? Okay. So once you understand this, then here actually the important aspect here it is minus del square phi is nothing but q dot del dot q. Del dot q, this is equal to 0 for an incompressible fluid. So this is 0 for an incompressible fluid. Then, so if this is equal to 0, then it will be a possible form of liquid motion. So if this is equal to 0, this is del square phi. So this is f double dash of r plus 4 times of f dash of r divided by r. This is equal to 0. Got it? This is equal to 0. So note down till this point, I am going to erase it. And then if this is equal to 0, then you can identify the function f. That's what is our task. So you have to identify the function f value based on this equation. Once you identify the function value, then you are going to identify the constant speed lines as q square, where q is equal to minus del phi, where phi is nothing but x into f of r, where f is given by this equation. Got it? Noted down? Okay. So this value, as per the incompressible fluid, f double dash of r plus 4 times of f dash of r by r is equal to 0. It implies so f double dash of r divided by f dash of r plus 4 by r is equal to 0. So if you integrate on either sides, then this will be log of f dash of r plus 4 by 4 into log r is equal to log c. So then this will be r into f dash of r is equal to constant. Sorry, r power 4. R power 4 into f dash of r. So f dash of r is equal to c into r power minus 4. So this is f dash of r. But if you do this integration with respect to r, then this will be f dash of r into dr is equal to c into r power minus 4 into dr. Then if you integrate on either sides, then this will be f of r is equal to minus c into r power minus 3 divided by minus 3. Plus d. So c into r power minus 3 plus d, this is the function f of r. Got it? So these are c, d are the arbitrary constants. Got it? Yeah. So this you can keep minus 1 by 3 as it is. So that is the value of c. Now once you find the f of r value, right? So f of r value once you find out, q value actually we have identified to be minus del phi. So this value, what is the value of minus del phi? We have derived this already. So minus f of r into I minus x into f dash of r by r, f dash of r by r into r. So this is the velocity vector. Now the velocity vector, in that f of r you can substitute it. So f of r, q is equal to, so minus c by 3 into r power minus 3 in plus d into I plus x by r into f dash of r. F dash of r value we found it. So this is c into r power minus 4. C into r power minus 4. This is f dash of r into r bar. So this value is nothing but the velocity. Right? So he said that there is one condition, as r tends to infinite, q tends to 0. See, if r tends to 0, then, sorry, r tends to infinite, q tends to 0. If you substitute that initial condition here, r is equal to infinite, this part will be 0 and this part will be 0. If these two parts are 0, then what is left over is q is equal to 0 for di. It implies d equal to 0. So this is the initial condition. Then, if you substitute d is equal to 0 in the q value, so q value is coming out to be, q is equal to minus c by 3 into r power minus 3 plus x by r, so x by r power 5 into r bar. Right, into I. So this is the velocity vector, right? So once you get this velocity vector, if you want to identify the magnitude of this, then you can find out q dot q is equal to q square. Is equal to q square. This q square is nothing but the magnitude of the velocity square. So if it is constant, then definitely the magnitude of the velocity is anyway constant. So you have to identify from this vector q dot q value. That's it. Got it? So q dot q, you are going to get it as, so just note down this first. Then so the simplified form of this q value is q is equal to c by 3rq into 1 minus 3xr by r square. And this is I. Yeah, that is I. Now q dot q, c by 3r square r cube whole square into, so I dot I is 1 minus 3x by r square into r square. So this is c square by 9 r power 6. Yeah, c square by 9 r power 6. Then 1 minus I minus 3xr by r square dot product with I minus 3xr bar by r square. Now the dot product of this will be I dot I is 1 and I dot this and I dot this. This is minus 6 xr bar by r square, and then minus minus will be plus, and then 3x by r square whole square into r bar dot r bar. So this is c square by 9r power 6, 1 minus 6x by r square. So here actually, r bar dot I. So r bar dot I will be x. So this is x square plus 3x square by r power 4 into r square. So this r square times it cancels. Then this will be c square by 9r r power 6 into 1 minus 3x square by r square. So this is q square value. Got it? Sorry, this is 9. Then this will be plus. Yeah. So if you further simplify this, this is c square by 9 r power 8 into r square plus 3x square. So c square by 9 into r power minus 8 into r square plus 3x square. This is the magnitude of q square. Now this is equal to constant will give the constant speed lines. Yeah. Why q dot q? You wanted to identify the magnitude of the velocity. So the magnitude of the, so q is a vector, but the magnitude of the velocity has to be constant for constant speed lines. To identify, this is a shorter way. So you are identifying the q dot q, or else actually you can even find out the magnitude of the velocity vector q. But that is a little bit complicated because r and I both are involved here, right? R again involves I. So r is nothing but xi plus yj plus zk. And then you have to separate the I component separately and j component and k component. And then you have to identify the magnitude of q by squaring and rooting, right? So, but rather than that, it will be easier for us to identify q square, which is nothing but q dot q. So this is simple vector scalar multiplication that gives the most simplified result than the previous one. Yeah. But both are same and both are correct. But this is the methodology what we adapt. Clear? But if you notice in the entire process what we have done from the fluid dynamics point of view, what you have done is, so phi is equal to x into f of r. This was given. What we have identified is q is equal to minus del phi. And then del dot q is equal to 0. These are the only things from the fluid dynamics point of view. The rest of the things is simple vector calculus which you need to follow just to solve and prove the result whatever he asked for. So here actually this is the q vector we have got. I have just done dot product again with the same thing. So then c by 3 r cube whole square and then square it. Square is I square, but the square is with the dot product I dot I, right? So I dot I is equal to 1 and then minus 2ab minus 2 into I dot r. I dot r is nothing but x. 3x by r square into 2, that is 6 into x by r square into r bar dot I. So r bar dot I you can replace in the later section as x. So x dot x is x square. And then here b square. B square is nothing but the square of this. Square of this with r bar dot r bar. So 3x by r square whole power 2, that is 3x by r square whole square into r bar dot r bar. R bar dot r bar is r square and this is r power 4. I'll cancel 1 r square. Then 9x square by r square is left over. Then here also minus 6x square by r square. The sum of these two will be 3x square by r square, 1 plus. q square is equal to c by r power 6, c square by 9 into r power 6, 1 plus 3x square by r square. And this you can further simplify by taking this r square out. So r square plus 3x square divided by 9 into r power 8 I have taken out. That's it. And this I have written on the numerator as r power minus 8. Anjali, got it? Yeah. So any questions on this? Only thing is, you have to, without having any mistake, you should be able to find out dou phi by dou x and dou square phi by dou x square. Similarly, dou square phi by dou y square and dou square phi by dou z square. That is the complexity here. But that is complex because both r and x is involved. That's the difference. If q square is equal to constant, we'll give the, so this is considered constant. We mean what he said was, he asked us to prove that q square is equal to constant is required to take. Why? Because he asked us to prove that the speed, constant speed lines are given by this equation. So the speed lines is given with this equation. If it has to be constant speed, then this has to be equated to 0. Sorry, equated to constant. Q square is equal to C will give the constant speed lines. That is the statement you have to make it. Here, any questions? Oh, yeah. So that's all for today. In that, so next class, I'll try to solve some problems on this one, on vorticity and vertex lines, and then we'll go to the Bernoulli's equation and Euler's equation. Yeah. So till then, good morning. Yeah. Thank you. Bye bye.